Hey Mirage, I got some trash for you.
Good thing I got a trash can.
We designed an automated trash can. But why? In today's world, people interact with many things every day, which makes it easier for bacteria and germs to spread. In your trash bins, all the trash you collect throughout your entire house, it is one gigantic bacterial breeding ground. So we decided that our objective was to design and implement an automatic trash can that will improve hygiene and odor management. And our desired area of application is every household in the world. And through this, even if it's a small margin, it will decrease bacterial spread throughout the entire world. So now for the actual design. So looking at a trash can, the first point of contamination is the lid. So we decided to change that. We wanted to make it contactless, where we would use an actuator to move the lid by itself, and you wouldn't have to open it every time to throw out trash. And the actuator would be a servo motor. This is the exact model we used, the MEM261. We utilized 5 volts, and per motor it weighs 7.8 ounces. We chose this motor because we knew it would have a strong enough torque to be able to raise the lid, and these motors operate to move to a specific angle. The other motor types that could have been utilized were steppers and DC motors, but both continuously move in full cycles, which is not desired in this type of project. To signal to the motors to raise the lid, we use an ultrasonic sensor. The ultrasonic sensor would detect the position of a person in front of the trash can, and it would signal for the motor to move to a specific angle, and that angle correlates to the lid being opened. And the signal is pulse width modulation, where the time it takes for pulse to repeat or the frequency determines the angle. So we eliminated excessive contact with the contaminated lid, but now how about the actual bacteria living and growing inside the actual bin? And for this, we decided to integrate a ventilation fan, and this ventilation fan is signaled by a humidity sensor inside the actual base of the bin. This sensor operates from 3.3 to 5 volts. Alongside the ultrasonic sensor, the humidity sensor also sends digital signals to the microcontroller, which in our case is the Arduino Mega. And then from there, these signals developed inside the Arduino are then transferred to the actuators, the servo, and the ventilation fan. And also an H-bridge motor driver is also needed to operate the ventilation fan. It is directly supplied 12 volts from a power source. Ideally, it should be from an outlet in real-world applications. This is the overall structure of the system and all the components involved. As you can see, we have the 12 volts supplying the H-bridge motor, and we also have the microcontroller supplying it to the sensors and the servo motor.
Our ultrasonic sensor sends digital pulse width signals to the Arduino, which we continuously sample as part of our closed loop system to detect when someone approaches. The humidity sensor gives us either a digital or analog signal, which we read through the Arduino's ADC. Using this feedback, the Arduino runs a control algorithm to output PWM signals to the servo and drive the fan through the H-bridge. All the sensors and the servo are powered directly from the Arduino's 5 volts, while the fan gets its power through the H-bridge driver so we can safely handle higher current. Everything shares a common ground, which makes data acquisition reliable and keeps our system stable. This setup lets us fully integrate all components and ensures smooth system integration between sensors, actuators, and the controller. The sensors send their signals to the Arduino, where the controller samples the data and interprets the feedback. The ultrasonic sensor's pulse width tells us how close someone is, while the humidity sensor tells us the moisture level inside the trash can. The Arduino then generates PWM actuation for the servo to open the lid, and sends digital or PWM signals through the H-bridge to control the fan. We use an H-bridge to drive the fan because the Arduino alone can't handle the current. The H-bridge lets us do both simple on and off control and PWM-based speed control, so the fan responds dynamically to humidity changes. This makes our actuation safe, precise, and reliable.
And additionally to the design, we added mesh on top of the fan so no trash would enter into the fans while operating. We also use coffee stirrers as scaffolding to attach to the servo motor to extend its grip. By extending its grip, it would require less torque and moment on the motor to raise the lid.
For the fan control, we use the hysteresis model where the fan turns on above a set humidity threshold and off below a lower threshold to prevent rapid toggling. For testing trials, we set the difference to 2 units for fast troubleshooting. The lid uses the simple distance-based threshold. When the measured distance from the ultrasonic sensor is less than a defined value, the servo motor is actuated to open the lid. These thresholds act as set points in our feedback control system.
The system has 3 primary states: idle, lid open, and fan active.
In idle, the sensors are being sampled but no actuation actually occurs. When the ultrasonic sensor detects the proximity, the servo motor opens the lid, transitioning to the lid open state. If humidity then exceeds the set point, the fan turns on via the H-bridge, entering the fan active state. The system returns to idle once the conditions normalize again. The feedback itself from the sensors actually is very important to this project, as it basically systematically sustains everything. The ultrasonic sensor, for example, provides distance feedback, so we know when to actually lift the lid the Arduino uses to determine that. And then the humidity sensor is used to provide moisture feedback. It goes back to the Arduino and then controls the fan and turns it on. This sensor to actuator feedback ensures the trash can makes sure it actually reacts in real time to environmental conditions, making our system adaptive and efficient. Now, how does the code actually work? The code defines the state variables for the fan operation, where the lid is, and object detection, which allows the Arduino to track system status over time. Functions, for example, like run fan, stop fan, open lid, close lid, encapsulates the actuation logic, keeping our control algorithm modular and clear enough to actually reflect on, make sure everything's correct, and read. The fan, for example, uses PWM via the ENA pin of the H-bridge, while the servo receives PWM signals in its dedicated pin that it itself has. Both are controlled programmatically, however, based on the sensor feedback. The ultrasonic sensor reading is converted into distance in centimeters using the pulse of the actual echo signal. And this value is compared to the lid threshold for actuation. Finally, our OLED display is just updated each loop with our data from the Arduino, real-time data including humidity, temperature, distance, if there's an object detected and then checked off or not, and lid status, open or idle, providing a visual feedback interface so we can actually monitor the system's behavior.
Real-time data is displayed throughout the entire lifespan of the system, from humidity to temperature to distance of the ultrasonic meter, and also there's a symbol indicating whether or not there is an object being detected or not. A challenge faced with the entire construction of the trash can was the taping of the servo motor to the lid, and it would decrease the angle at which the box opened. The next version of this trash can would include a 3D printed bracket that would connect the servo horn to the lid. The servo horn would pierce into the cardboard.